right, so we're going to pick up where we left off with the fate of pyruvate by moving into what happens to the acetyl-CoA that gets that arises, the acetyl-CoA that arises from pyruvate. Hint: everything gets converted into carbon dioxide. So if we take a look here, first of all we took glucose and we did glycolysis to generate two of these 3-carbon products, which is pyruvic acid or pyruvate. So glucose was C6, pyruvic acid is C3, and then if you recall, in the presence of oxygen, we could convert this pyruvic acid into acetyl-CoA with loss of CO2. So now we're down to acetyl-CoA, and that was covered in the last lecture, plus CO2. And if you look, now we went from C3 down to C2 because we lost one of the carbons as CO2 from the pyruvic acid. And so now what we're going to do is look at the citric acid cycle, the tricarboxylic acid cycle, or the Calvin cycle, however you want to describe it, to convert this into 2 CO2s amongst other things. Okay, so what we're first going to do is take our acetyl-CoA and react it with oxaloacetate. So acetyl, and let me just label this first of all. So we have the citric acid cycle, also called the TCA for tricarboxylic acid or Calvin cycle. Okay, so what we're going to do here is start out with this molecule oxaloacetate. Okay, so this species, and we're going to react this with acetyl-CoA. Going to react this with acetyl-CoA, followed by and with hydrolysis. Okay. I guess I could spell this out a little bit better. What we're going to do is an Aldol reaction where everybody can show you the overall diagrams. Let's have some curly arrows to lend some credibility to the products here. Going to do an Aldol reaction where we add the enolate or an enolate equivalent of acetyl-CoA to that ketone of oxaloacetate. That's going to give rise to this species where we have a new bond formed at this position, from the alpha position of CoA to the reactive ketone. Now the other things attached to the oxaloacetate, which are 2 acids, I should draw that normal font, sorry. Those are not reactive as in an aldol process, so we just kind of show them coming along for the ride. But that blue bond is our new bond. And then at this point, we're going to have some sort of hydrolysis process coming in where water comes in and SH-CoA comes out. That's just converting that thioester into a regular carboxylic acid. Now the product of this is, we're going to let this react with an H plus up here. So we have an OH in the center. That OH was bound to a carbon with a CO2 minus. CO2 minus over here from oxaloacetate. And now our thioester is also a carboxylic acid. Okay, so if we look at this structure, CO2s on either side, a CO2 in the middle with an OH, this is citrate, or if you add 3 H pluses to it, it's citric acid. Hence the citric acid cycle. So acetyl-CoA interacts with this molecule oxaloacetate that's lumbering around ready to engage in the cycle to make citrate. And it's from here that we use the oxaloacetate starting material to generate our 2 carbon dioxide molecules from acetyl-CoA. Okay, so how does this work? Well, in the first step, what we're going to do is dehydrate and then rehydrate. So this is accomplished in the active site of a single enzyme, where we're going to dehydrate, and by that I mean we're going to lose water. So you could lose water here. A few ways you could draw it. There's some protonation states too that kind of complicate things. But we're going to get something that looks like this. Okay. So we dehydrated the molecule by pulling off the alpha position, the alpha proton, to one of the carboxylic acids on the ends, and then kicking off the OH. Now we're going to have some sort of easy selectivity, which I'm not depicting, but then we're going to immediately, it turns out to be not too consequential to us. The enzyme knows what it wants, but we're going to dehydrate and then rehydrate, where we add the water back in. This time it's going to add, just in the opposite reaction, it's sort of like a Michael-like reaction. It's going to add to the beta position of this alpha-beta unsaturated carbonyl. You could generate a carboxylate enolate. All of this, again, facilitated by enzyme, which takes care of the negative charges. What this means to you is that the negative charge through that dehydration, the oxygen through that dehydration, rehydration step moves from the central position to being next to one of the CO2 minuses. And this is isocitrate. Citric acid is achiral, isocitrate is not. So we now have stereocenters defined. And in this orientation, this is going to be a dash. So the enzyme is just going to pick on a specific isocitrate, a specific enantiomer of isocitrate. Now at this point, what we're going to do is we are going to oxidize this alcohol. The oxidized alcohol will form a ketone, alpha to that carboxylic acid. Carboxylic acid's not anything to worry about at this point, but the one that was in the center, the central CO2 minus, which I'm now going to draw explicitly, is able to decarboxylate to form an enolate, which is rapidly protonated. So we get decarboxylation here, stabilized by that ketone. This decarboxylation wasn't possible from the alcohol form, but because we can generate an enolate after decarboxylation occurs, the CO2 is now possible. This is the first of our decarboxylation reactions that takes place. You'll notice that the atoms that we use for acetyl-CoA are up here. My point is we're not actually pulling off the CO2 from the acetyl-CoA atoms. It just balances that you lose 2 CO2s as a result of this process. The acetyl-CoA atoms are up there. So after decarboxylation, so we're going to lose CO2 as a neutral, we get an enolate at this position, which is rapidly protonated. And by enolate, I mean, you know, it's probably protonated right away in the enzyme active site, but we can go ahead. So what we're doing is we're replacing the CO2 minus that was alpha to that ketone with an H. And so we get to this molecule called alpha ketoglutarate. Okay, we know it's glutarate because, oh my, such good apple pie. We kind of talked about this in organic too. O for oxalic acid has 2 carbons. So we're at 1, 2, 3, 4, 5 carbons. O is 2. My, such good. G is glutaric acid. And so we have, yeah, anyway, this is a cool intermediate because if you react this with PLP and you aminate that alpha keto acid, you form glutamic acid, the amino acid, okay, or glutamate. So pretty cool intermediate. But anyway, we're not done yet. We've only lost 1 CO2, right? So we need to lose a second one. So at this point, we're going to convert the carboxylic acid closer to the ketone with into a thioester using, let's see, let me just make sure. Oh no, we actually lose the second CO2 at this stage too. That's my fault. Okay, so at this stage, we are going to decarboxylate this molecule and oxidize the resulting product. And we should look at that one more carefully. So that's going to convert this into that carboxyl group at the end into a thioester. And again, sorry to go through the detail too quickly there. But there's our second CO2 molecule. Now the rest of the tricarboxylic acid cycle is going to be converting our this structure, which is succinyl-CoA, back into our starting structure, oxaloacetate. And so what you do there first is you convert this into a dicarboxylic acid. So we have net water addition here. Now I'm simplifying things quite a bit just to get us a carboxylic acid from the thioester. So now we're at succinate. Oh my such, we're at 4 carbons. We've lost a carbon. Succinate. And now what we're going to do is desaturate that, much like we did with the beta oxidation of fatty acids using FAD. So FAD is going to rip 2 hydrogens out. That's going to give fumarate. Okay, and that's a process similar to what we saw in that beta oxidation. Now, fumarate has, with that alkene, can now accept water in kind of a Michael-like addition, where our conjugate addition, where we add the nucleophile to the beta position. And it could be either one of the beta positions or either one of the alkene sides, because both of them are actually beta to one of the carboxylic acids on either side. But we're going to get a specific one. So this is going to be a wedge in this depiction, because enzymes will control the enantioselectivity. And that's going to give us S-malate, okay, or malic acid if you want to protonate it. But then that just needs to be oxidized with some NAD+, oxidizing the alcohol into a ketone. And that particular alpha keto acid is the oxaloacetate starting. Okay, so I want to get into step 4 here, which is the decarboxylation event. Let's see. Huh. Oh, I see. I think I see. Yeah. Maybe I don't see. Huh, okay. Well, I'm gonna have to get back to you on the details for the conversion of the alpha ketoglutarate into succinyl-CoA. The book kind of has a vague description of it. Maybe I'll just do a Google search while you're writing this down. So alpha ketoglutarate to succinyl-CoA. Looking for curly arrows. All right. Well, I'll get back to you. I don't want to waste any more of your time. Okay. So we'll call this one done here. I may add a supplemental lecture so we can look at. Oh, I got it here. It's a TPP reaction. Okay. No problem. No problem. No problem at all. What we do is if we want to get from, sorry, I got it here. Okay, I don't know why the book doesn't go through this. I guess, you know, that's why we have this class, so we can supplement the book here. What we're going to do is add, much like how we got from pyruvate into acetyl-CoA, we're going to do the exact same type of chemistry. That is, we have an alpha keto acid. We need to react this with TPP. This is going to be a lot like the last lecture, where we've got some R group up here, plus charge on nitrogen, negative on carbon. So that's going to add here to give us this species. Now we have a nitrogen still with a positive charge. We have the rest of our chain. Well, I'll spell that out. Let's not shorthand that. Okay, so 2 carbons to a CO2 minus. Okay, so what we can do now is pick up a hydrogen atom on the O minus, and that's going to add here. So then we have CO2 to OH. The thiamine diphosphate counterion is still positively charged. And then now what we do is we decarboxylate. I'm going to write that CO2 minus out more explicitly. So we're going to come here, going to come here, and push up here. That's going to give rise to a now neutral heterocycle. And we're going to lose CO2. So there's our last CO2 that's lost. If you look, our acetyl-CoA atoms are still hanging out over here. And they ultimately get absorbed, unless, I mean, I guess there's some symmetry in here where it could be either side, but they ultimately sort of, get absorbed into the oxaloacetate, which is the final starting material. Okay, so now what we can do at this point is we're at an aldehyde oxidation state, and we did know that we had to do some sort of oxidation step to get to the final product. So there's a few ways we could go about this. And we're neutral at this position, shoot, neutral here. Okay, but we're not aromatic. So what we could do is have an H plus here. Which gives us an aromatic heterocycle, now positively charged. And then we could lose this H plus to reestablish our TPP. Which is our catalytic cofactor. And at this point, we do oxidation. Which proceeds with looks like just NAD plus. And that's going to convert the alcohol into a carboxylic acid Well, I guess we probably engage the thioester. Okay, anyway, let's just go thioester here plus co-ash. I'm guessing we probably don't have much of the full aldehyde equivalent, but we can get there. We can at least see where the thioester gets involved, which is from the TPP adduct after we do the decarboxylation event. So thioester may be here. Sorry, I didn't have my notes updated. I thought the book had that laid out in front of me. Okay, anyway, so that's the Calvin cycle, the citric acid cycle, the tricarboxylic acid cycle. Hopefully you found this helpful. Otherwise, we'll see you next time.